Hello, welcome to Fundamentals of Acoustics. Today is the last day of the 6th week of this course, and what we will do today is essentially a continuation of what we were doing yesterday, that is discussion on Kunst tube. And the first part of this lecture will be essentially summarizing whatever we have discussed in terms of impedance for open tube, closed tube, as well as the Kunst tube. And then in the second part, what we will do is we will also go back to spherically propagating waves and compare the the impedance of a radially propagating wave with that of a planar wave. So, that will set the ball rolling for more detailed discussion on spherically propagating waves, which we will restart in the next week, that is week 7. So, in the first part of this lecture, we will develop a summary. So, we had discussed a closed tube, then we had discussed an open tube, and then an semi-infinite tube. Okay. So, we will summarize for these systems the value of z, eta, rho, and also the magnitude of gamma. So, closed tube, then we have open tube, and then we have finally semi infinite tube. So, what we will do is we will construct a table for Z, which is specific acoustic impedance, eta, rho, and rho is the ratio of maximum pressure amplitude and minimum pressure amplitude as I travel in the tube, and then finally gamma. So, for a closed tube, this is infinity, z is infinity. Why? Because z is defined, so actually this is ZL, so it is the tube so x is equal to 0 and this is ZL. So, ZL is 0 is infinite because the complex amplitude of pressure is non-zero and complex amplitude of velocity is 0. So, this is infinite, but it is not a real number, it is an imaginary number. It is an imaginary number. So, if I plot it on a complex plane, it will be positioned at an infinite distance from origin, but on the y axis. Then we look at eta, and this is equal to 2 omega d min divided by c minus pi. Now, d min is the location where pressure is going to be minimum, okay, where pressure is going to be minimum, and if we do the math, so in this case d min will correspond to half of the wavelength of the system. So, if I put in d min as lambda over 2 in this equation, then this entire term 2 omega d min divided by c comes to be pi. So, pi minus pi is 0, okay. And then rho is the ratio of maximum pressure amplitude divided by minimum pressure amplitude. So, maximum pressure amplitude is non-zero and minimum pressure amplitude is 0, which is at the at some specific location. So, this is infinity, and then gamma. So, gamma was defined as P minus over P plus, and for a closed tube the this ratio P minus and P plus is 1, P minus is equal to P plus. So, it is 1. Okay. For an open tube, the value of ZL is 0 because pressure at the open end is 0 while the velocity is non-zero. So, 0 divided by non-zero entity is 0. Eta is negative pi, and it is negative pi because the value of d min is 0. When d min is 0, then eta becomes negative pi. The ratio of, so this rho ratio, which is the ratio of maximum pressure amplitude divided by minimum pressure amplitude. Maximum pressure amplitude is some number, but minimum it goes down to 0. So, this is infinite, and then the value of gamma for an open tube, it is P plus equals negative of P minus, but I am taking just the absolute value. So, it is still 1. And then for a semi infinite tube, this is rho naught C, and all these terms, they are not necessarily relevant in context of this table. So, this is the discussion in context of impedance, and the next thing which we will do today is we will compare of impedance for a radially propagating wave. So, I will call it Z radial, and a planar wave, which is typically a wave which is travelling in a duct, and if the duct is infinitely long, then it will be Z planar. So, Z radial divided by Z planar. So, this Z planar is Z for a 1D wave in a Cartesian frame for a semi infinite tube. Okay. So, this ratio is what? So, Z radial is j omega r divided by c plus j omega r into Z naught, and Z planar is Z naught. Okay. So, this Z naught cancel out. So, I am left with 1 over 1 plus c divided by j omega r. So, this is equal to, if I take j on the numerator, I get 1 minus j c divided by j, divided by omega r. Now, c over omega equals, so c is frequency times wavelength divided by 2 pi f. So, this is equal to lambda over 2 pi. So, this becomes 1 over 1 minus j times lambda over 2 pi r. Yeah. So, while we are doing this, we must remind ourselves once again that z planar we are taking as z0, because what we are comparing it with is it is the z for a 1D wave in a Cartesian frame for a semi-infinite tube. For a semi-infinite tube z planar, so those are planar waves and the impedance is same as z naught. We had developed that relation earlier in last couple of classes. So, if it was a closed tube, then this z planar will change, but for a semi infinite tube it is same as z naught. Okay. So, it is z 0. No, but so I am just equating this z planar as z naught, and I have explained that z planar is in context of a semi infinite tube. I have written it here. Okay. So, this is there. So, then the ratio, so if lambda over 2 pi r is very small compared to 1, or if lambda over 2 pi is very small compared to r, then z radial divided by z planar is equal to 1. Okay. So, what we will do is we will actually do an example and get a feel of what this means. So, we will do an example. So, we consider that frequency is 100 hertz and we know that velocity of sound is 345 meters per second. So, lambda comes to be 3.45 meters. So, lambda over 2 pi equals 0.5491. Now, z radial divided by z planar, if I have to find its amplitude, it is equal to 1 over 1 minus lambda over 2 pi r j. So, I have to take the amplitude of this entire thing, and this is equal to 1 divided by 1 plus lambda over 2 pi r whole square, and the entire thing has to be put under a square root sign. So, we know that lambda over 2 pi is 0.5491 if f is 100 hertz. So, we will compute, we will construct a table that if we are at a distance of 10 centimeters away, we will calculate the value of lambda over 2 pi r. Then we will also calculate 1 plus lambda over 2 pi r whole square, and then we will calculate z radial by z planar, its magnitude. So, when r is equal to 10 centimeters, this term becomes 5.49, this is 5.48, and this works out to be 0.179. So, when you are 10 centimeters away from the source for a 100 hertz wave, the radial impedance and the planar impedance are not more or less, they are significantly different. Let us see what happens at when you are 1 meter away. So, this becomes 0.549, this becomes 1.141, and the ratio of radial impedance and planar impedance, it becomes 0.876. So, it is reasonably close to 1, it is about 88%. They are, but if we are 10 meters away, then this becomes 0.0549, and the number under the square root sign becomes 1.002, and the overall ratio becomes 0.998. Okay. So, lambda is 3.45 meters, this r is about 10 meters. So, if roughly if we are 3 times away from the source, if we are 3 times away from the source compared to lambda, then the impedance for the radially propagating wave is pretty close to that for a planar wave. So, the point is that this condition that lambda over 2 pi r should be very small compared to r does not necessarily mean that this whole thing has to be extremely, this r has to be extremely large in an absolute sense. What matters is that this term lambda over 2 pi r should be, and actually not just this, actually its square should be very small compared to 1. So, even if it is a moderately small number, when I square it, it becomes even smaller and I get this kind of a result. So, this concludes the discussion for this week, and in the next week, which is the 7th week of this course, we will start discussing radially propagating waves in far more detail, and that is what I look forward to. So, I hope that you have a wonderful weekend. Please do review whatever we have been talking and discussing over these last 6 weeks. This is a week, this is a course which is 12 weeks long. So, we are more or less halfway through the course. So, this is an important milestone, and I would specially encourage you to go back and review all the concepts and details which we have discussed over these lectures on these last 6 weeks, and that kind of a review will be extremely helpful to what we will discuss in the second half of this course. So, with that, I once again hope that you have a great weekend, and we will meet once again on the coming Monday. Thank you and have a great day.